Good day, grade 12s. Welcome to week 11. In the next couple of lessons, we're going to be looking at work, energy, and power. In this lesson, we're going to specifically be looking at work. So what is work? Work is done when a force acts on an object and the object moves in the direction of the force. So we have to have a force, it has to act on the object, and the object has to move in the direction of the force. Okay, please remember that. So the formal definition of work is work done on an object by a constant force is defined as F delta x cos theta, where F is the magnitude of the force, delta x is the magnitude of the displacement, and theta is the angle between the force and the displacement. Okay, so we've got F delta x cos theta equals work done, where F is how much we're pushing it, delta x is how far it is moving, and cos theta is obviously working out the angle that we're pulling it or pushing it at, okay, because that makes a difference as well. So please understand this, and you need to know the definition very well, okay, that work done on an object by a constant force is defined as F delta x cos theta, and you need to know that F is the magnitude of the force, delta x the magnitude of the displacement, and theta the angle between the force and the displacement. Please make sure you learn it. What's important is that work is a scalar quantity. So what does that mean? It means that you cannot have a negative value. You cannot have a negative value. Okay, you cannot do negative amounts of work. And why is that? That's because work is a transfer of energy, and energy cannot be negative. Finally, the unit for work is the joule, okay, or the Newton meter. And where do they get that Newton meter from? Well, if you remember, we know that work is equal to F delta x cos theta. Cos theta doesn't have a unit, but F is measured in newtons and delta x is measured in meters. So the work done is Newton meters, or better still, we know it as joules. So when is no work done? We just said that the definition of work was when a constant force was applied and the object was moved a distance and it was in the same direction as the force was applied. So therefore, if a force is applied to an object but the object does not move, then no work is done on that object. As you can see over here, this person is pushing this huge rock. The rock is not moving. So even though this person is straining away, they are pushing really, really hard. But even though pushing really, really hard, there is no work done on the object because the object is not moving. Also, when an object moves at a constant velocity across a frictionless surface, then there is no resultant force. Then there is no work done on the object. Okay, so let's think about what we said. We said work is equal to F delta x cos theta. But what you need to understand is this is actually F net or F resultant. And if there is no resultant force, then that number there is 0. Okay, let me just change that. Then that number is 0, and 0 times anything is 0, so therefore the work done is 0. So if there's no resultant force and the object is moving at a constant velocity, then no work is done. And those are two cases when no work is done, and those two are very important. Let's look at this example. Here we have little waiter, let's call him Harry, and Harry is carrying a tray. So now if you think about it, Harry lifts up the tray, and when he lifts up the tray, he's working against the force of gravity, okay? But once he's lifted it up and he's walking this way, he is carrying that tray in this direction, but he's holding it up. So do you see that the force that he's applying and the direction he's moving are at right angles to each other? And therefore, even though Harry's arm might get a bit small if he doesn't have a bit sore if he doesn't have very big muscles after carrying this tray for a long time, okay, he is doing no work. He is doing no work as far as science is concerned. So the weight is doing work against the force of gravity, but only as he picks up the tray and he puts it down. He's doing no horizontal work on the tray as the force he's applying is perpendicular to the direction of the movement. So as the waiter walks along, okay, with the tray on his arm, as he walks along, he's doing no work because the force that he's acting is upwards, but the direction he is moving is horizontal, and they have to be in the same direction in order for work to be done. Okay, and that's very important. So let's do an example. It says determine the work the boy does in pulling the child. Okay, so you can see that the boy over here is pulling at an angle of 30 degrees and he's pulling a distance of 30 meters. And you can see the child is actually traveling in this direction. So if we had to do this nice and slowly, if we had to say, okay, fine, by definition, we know that work equals F delta X, the net force delta X. I know that the definition's got a cos theta, and I want to show you where it comes from. So if we look at this diagram, we can see that the guy, the little boy, is pulling at 50 newtons, okay? But this 50 newtons is 30 degrees to the horizontal. And the horizontal is the direction that the little child is being pulled. So in order to get the net force that is actually pulling the child horizontally, we'd need to work out the horizontal component. So if we did SOHCAHTOA, and we apply the SOHCAHTOA to this triangle, we're going to have to use cos. We want the horizontal component, okay? So cos of theta is adjacent over hypotenuse. The adjacent is the force that we actually want, okay? And the hypotenuse is the force that the boy is actually pulling. So therefore, we can say that hypotenuse cos theta equals the side we want, the actual adjacent side. So what would that be? That would be 50 cos theta. So that's where this definition of F net cos delta X cos theta comes from. It's actually saying the work is defined as the net force times the displacement, as long as the displacement is in the same direction as the net force. In this case, the net force is F cos theta times by delta X. Okay, but we know that F in this case is 50. Cos theta is going to be cos of 30 degrees, and the delta, the displacement, is 30 meters. So it's times by 30 meters altogether. So then we whip out our calculator and we go cos of 30, which is going to be 0.87. So we go 50 times 0.87 times our 30 meters. So we multiply it by 1500. And we get that the work done is 1299.04 joules. The work done is 1299.04 joules. And remember, grade 12s, you always run around off to 2 decimal places, and you actually want to round off right at the end. So this, I would have just put all of this into my calculator, and you could have actually done it in the order that now that you understand where this cos theta is, you can just put it in this order. So in other words, if you were presented with this question in the exams, you would just go, well, we know that work done is equal to F net delta X cos theta, and you go, well, he's pulling with a force of 50 for a distance of 30 meters, and it is an angle of 30 degrees. And you substitute that in, and you get 299.04 joules. And that's all you would have to do. So in this question, which is very basic, you don't have to think at all now that you understand where this cos theta is coming from. Right.